Forget everything you thought you knew about how computers should work. We're reaching the limits of the classical clock-driven approach of using silicon chips. We're entering an era in which computers are beginning to mirror the biological intelligence of the human brain. How? Through neuromorphic chips. The machines we're used to never really rest. They tick and cycle, endlessly processing and evaluating instructions, even when there's nothing meaningful to compute. Your laptop, your phone, massive AI data centers, they're all constantly burning energy just to be ready. But your brain doesn't work like that. Your brain is mostly quiet until something changes. A sound, a movement, a thought. Then suddenly there's activity. And that difference is where neuromorphic computing begins. Neuromorphic chips aren't your typical processors. They learn, evolve, and adapt, promising a future of truly intelligent systems. What makes them so different? And why is this possibly the most important tech breakthrough you've never heard of? Let's talk about it. Before we get into the details, here's a key point. Modern AI, though powerful, is energy intensive, mainly because it uses the von Neumann architecture, which strictly separates memory and processing. This design choice is fundamentally different from how biological brains work, leading to resource-heavy computation. Large models process enormous amounts of data in dense, continuous blocks. They move information back and forth between memory and compute units over and over again. That movement is very much where most of the energy is lost. This is called the von Neumann bottleneck, and it's one of the biggest reasons today's AI systems need warehouses full of GPUs and megawatts of power. So here's the question. If natural intelligence runs at about 20 watts, which is about the power of a dim light bulb, why does artificial intelligence need a power station? That question has driven decades of research, and it leads directly to neuromorphic chips. Neuromorphic computing doesn't try to make today's computers faster. It asks a different question. What if we built computers that work like brains instead of calculators? Not metaphorically, architecturally. Instead of instructions and clocks and neurons. Instead of constant data flow, spikes. Instead of separating memory and computation, as in traditional computers, memory and computation exist together, as in brains. At the heart of neuromorphic systems lies a spiking neural network. Most people are familiar with neural networks from deep learning, that is layers, weights, matrices, and backpropagation. Spiking neural networks are different. Information isn't passed as continuous numbers, it's passed as events. A neuron fires, or it doesn't. The firing is called a spike. Neurons only spike when something meaningful happens. No spike, no computation. That alone changes everything. Let's see this difference in action by looking at vision systems. Most AI vision processes whole images, every pixel, every frame, many times each second, even when nothing changes, using a load of energy in the process. For example, traditional surveillance systems cameras require 2 to 5 watts of power to analyze full images at 30 frames a second. Research on neuromorphic vision systems, such as event-based cameras, has shown power consumption as low as 30 milliwatts in similar situations, or over 100 times lower. For example, a 0.03 watt compared to a 3 watt. Instead of processing each frame the same way, a neuromorphic vision system only processes the changes. Rather than asking, what does the whole world look like now? It asks, what changed? A shadow moved, an edge shifted, something entered the frame. Only then does it respond. This lets these systems react quickly while using much less power, much closer to how living things see. When built this way, hardware becomes something new, faster, low power, and always on. Beyond vision systems, The same idea matters for robots needing to adapt quickly, smart devices where energy saving matters, and wearables that run on little power. All benefit from event-based processing's energy saving and fast reaction. Systems that are fast, low power, and always on. Now let's talk about architecture. Traditional chips are clock driven, meaning operations synchronize with a central clock cycle. Everything happens in lockstep. Every cycle, every unit steps together. Neuromorphic chips are asynchronous, meaning that computations occur when events happen, not according to a uniform clock. Instead, events propagate when they happen, like messages traveling through a network. If one neuron fires, it sends a spike. That spike triggers other neurons. Those neurons may or may not fire. This makes neuromorphic systems incredibly good at real-time reaction. There's no waiting for the next clock cycle. No batching, no buffering, unless you choose it. Another core difference is that unlike in traditional machines, memory and computation are integrated on neuromorphic chips. In most computers, memory and compute are separate, with data constantly moving back and forth between them. In neuromorphic chips, synapses are memory. They store weights locally, right where computation happens. So instead of dragging data across a chip thousands of times, the chip lets physics do the work locally. Less movement, less energy, less latency. This is one of the biggest reasons neuromorphic chips can be orders of magnitude more efficient when used correctly. And that last part matters. According to a 2025 article by Stephen Abro, apologies for any pronunciation there, and some colleagues of his, neuromorphic computing is not intended to directly replace GPUs, but rather offers an alternative approach. While traditional large language models are not well suited to neuromorphic hardware, the authors describe the architecture specifically adapted for Intel's Loihi 2 that achieves up to 3 times higher throughput at half the energy compared to the costs of running transformer-based LLMs. This hardware isn't designed for dense matrix maths at massive batch sizes. It shines in a different regime. Streaming data, sparse signals, real-time environments, edge devices, robotics, autonomous systems, always-on sensing, and low-power intelligence. Now, let's ground this in reality with some actual hardware. Over the last decade, multiple serious neuromorphic platforms have emerged. For instance, Intel's Loihi or IBM's TrueNorth and BrainChip's Akida are prominent projects in the field. These platforms explore different trade-offs, but all share the same core ideas: spikes, events, locality, and sparsity. Some are digital, some are analog, some are hybrids. One class of systems focuses on large-scale digital neuromorphic cores designed to efficiently simulate millions of neurons. Another approach focuses on analog neuron dynamics, where electrical circuits mimic biological neurons and can sometimes run even faster than real brains. Others focus on edge deployment, pairing neuromorphic compute directly with event-based sensors. These chips exist, but they run real workloads. They don't just look like your laptop quite yet. Now, let's talk about training, which is a big challenge for neuromorphic computing. Unlike regular deep learning models that used well-developed training methods like backpropagation, most neuromorphic systems don't have an equally efficient way to train. The main problem is that neuromorphic hardware operates on spikes and events, whereas deep learning relies on gradients. Because of this, many current solutions use hybrid models. They train neural networks on GPUs, then deploy the learned weights on neuromorphic hardware for running tasks. This process can cause mismatches and, at times, lead to lower performance. According to a recent study by Loihi, biologically inspired training rules like spike timing, dependent plasticity, have shown promising results, such as achieving about 87% accuracy in image recognition tasks when trained with larger data samples. These approaches, however, have been historically considered as less scalable or reliable than backpropagation, and have often required greater amounts of label training data or more frequent manual intervention to guide the learning process for complex tasks. There's also no standard, reliable way to train deep spiking networks yet, which makes it hard to use them for large practical problems. So, training directly on neuromorphic systems remains an open problem and a significant barrier to wider adoption. Researchers are exploring new ideas like surrogate gradients and neuromodulatory methods, but there hasn't been a breakthrough just yet. For now, it's unrealistic to expect neuromorphic chips to fully replace established frameworks, but if we think of neuromorphic hardware as part of a hybrid system, using GPUs for training and neuromorphic chips for running and adapting, then there are real opportunities for progress. This brings us to the real opportunity. The future isn't one architecture winning, it's orchestration. Just like modern AI systems combine multiple models and tools, future AI systems will combine multiple types of hardware. Dense compute, where density matters. Events-driven compute, where timing and efficiency matter. Brains don't use one neuron type for everything. Why should machines? And this reframes the original claim. Neuromorphic chips do not think like humans. They lack reasoning and semantic understanding, but they do process environmental change in ways that closely mirror biological processes. For example, imagine a neuromorphic microphone is used in a security system. When the environment is silent, it only activates its processing when it detects a significant event, such as a sudden glass break or alarm, instantly recording and analyzing that sound. By contrast, a conventional microphone constantly samples and processes all ambient sounds, even when nothing notable occurs, expending energy continuously. This concrete distinction clearly demonstrates how neuromorphic systems excel at responding to meaningful changes with high efficiency. They adapt to local events and minimize unnecessary energy use by default. As computing advances towards edge intelligence in fields such as autonomous vehicles, wearable AI, robotics, and smart infrastructure, these efficiency-oriented traits become more significant than simply maximizing raw processing power. The next era of computing will be faster, quieter, and more selective, more contextual, more aware of when not to compute. Imagine small devices running AI tasks using less than 1 milliwatt of power. The real promise of neuromorphic chips is not to replace current AI systems, but to change how we build intelligent machines, so they work better in the real world and adapt more easily. Also, studies comparing neuromorphic chips to conventional hardware, such as GPUs, show that neuromorphic systems can save substantial power for certain tasks. For example, in tasks such as sensing and edge computing, these chips use much less power, providing real-world numbers that show their potential advantages over other designs. These comparisons help show how much neuromorphic technology could change modern computing. They're about giving intelligence a new physical form, one designed for the real world instead of just data centers. Once you understand this change, it's clear how important this is for the future of computing.